So welcome back everybody, and we've just completed on video 2 the shear force diagram, and we found the maximum shear force, and we also seen that there were points of zero shear which indicated maximum bending points, and we then took one of those as being an additional critical point on the beam, and we drew another construction line in there and we give it another reference point called A1. So the next step then is to draw our bending moment diagram. Before we can actually draw our bending moment diagram, we will have to calculate our bending moments. So initially, to start with, I'm going to draw again a horizontal single line, and at each end of that I'm going to put in, well, I would do, it's the right thing, I'm going to put in a 0, because again this horizontal line represents a line of zero bending within our diagram and does not represent the actual line of the beam itself. So we need to keep that in mind whilst we're doing that. When we go to draw our bending moment diagram, everything above the zero line will be negative bending and everything below the zero line will be positive bending. So again, something to keep in mind. Before we can actually calculate our draw the bending moment diagram, we need to calculate the bending moments. So we're going to go and actually do that straight off. Initially, what I want to point out is that we will have to calculate the bending moment for A, A1, B, C, and D in that order. And then we will transfer those onto our bending moment diagram and draw the bending moment diagram and obviously find the maximum bending moment. So initially, to start, I'm just going to put up a wee heading. Calculating our bending moments. So the first one we've got to consider is the bending moment at A. In order to calculate the bending moment at any point on the beam, we need to ignore everything to the right of that point and consider only the forces or loads to the left of that point. And we will calculate moments for those forces or loads to the left of the point, and clockwise moments will be considered positive and anti-clockwise moments will be considered negative. So obviously, if you are in a position there, and I'll just drag this back up, to look at our diagram, if we're considering point A, then we can ignore everything to the right of A, which is all of the beam, and consider only to the left, which is absolutely nothing. So obviously, then we should realize very quickly that we couldn't possibly have any moments, and therefore the bending moment at A will be 0. Bending moment at A1, which is our next position, and if we go back up and take a look at point A1, we can ignore everything to the right of A1, consider only the loads or the forces to the left, which is going to be this reaction at A and this portion of UDL between A and A1. The scenario then really is that we don't have a distance so that we can calculate moments here. And the distance that we're after is this distance here. And I'm going to call that x. That distance is very easily found by taking the height that we're actually up here, or the amount of force that we've been pushed up to 34.67 kilonewtons, and dividing that by the gradient or the slope of this line. We know the slope of this line because we were pushed down by 12 kilonewtons per meter as we travelled along here. So the slope of this line must be 12 kilonewtons per meter. So in order to actually calculate x down here, then we simply take the starting force of 34.67 divide that by that gradient, which is 12, and that equals for us 2.89 meters. So that now calculates that distance for us. X equals 2.89 meters. And that allows us to now come down and calculate this bending moment at A. My suggestion always is to redraw a little diagram which represents that portion of the beam. It's a bit rough, I apologise. And we have reaction A, which is equal to 34.67. This is point A1. We've got this portion of UDL we need to consider, which is 12 kilonewtons per meter. And we now also know this distance. We just calculated that, which is 2.89 meters. And with every aspect of working with shear force and bending, where we have a portion of UDL and we have to calculate moments for it, then it is imperative that we actually convert that into an equivalent point load. So we've got 12 kilonewtons per meter, and it's over a stretch of UDL of 2.89 meters, and therefore if we multiply those two together we'll get a total load which turns out to be 34.67 kilonewtons, and that will sit halfway along that portion of UDL. So half of 2.89, which turns out to be 1.445 meters. And now we have everything that we need in order to calculate the bending moment at A. So we have ignored everything to the right of A1, bending moment at A1. We've ignored everything to the right of A1, and we've considered only to the left of it. So therefore clockwise moments are going to be considered positive. So what we have here clockwise is this reaction at A, 34.67, multiplied by the distance from the pivoting point at A1, which is 2.89 meters. So 34.67 multiplied by 2.89. We have no other clockwise moments, so we look then at anti-clockwise. Anti-clockwise moments are going to be considered negative, so I'm going to put a negative sign in there. And we have this 34.67 kilonewton converted point load, and it is 1.445 meters away from A1. So this becomes 34.67 multiplied by 1.445, and then we sum that up, and that sums up to be 50.10 kilonewton meter. And you'll notice that the units have changed now to kilonewton meter, and that is because we are multiplying kilonewtons by meters. And when we multiply those two together, the resultant units are kilonewton meter. Okay, so that has covered bending moment at A1. So we now need to take a look back up at the diagram again, and we're going to move across and we're going to calculate the bending moment at B. So we'll ignore everything to the right of B and consider only to the left hand side of B. Okay, so again my suggestion is that you would draw a small diagram to the left of B, just the same way as I did up above. So I'm going to leave you to do that. So in the calculation of the bending moment at B, we see that we have clockwise, again, the reaction at A, which was 34.67, multiplied this time by 4 meters because it is 4 meters away from point B. There are no other clockwise, so we then consider anti-clockwise, and I put a minus sign in because we consider anti-clockwise to be negative. And we have a converted portion of that UDL converted into a point load, so it's a 4 meter stretch of 12 kilonewtons per meter, giving us 48 kilonewtons of force. And it will sit halfway along that length of UDL from B back to A, which is 4 meters, so half of that is 2, so it's multiplied by 2, and that equals 42.68 kilonewton meter. So the next up then is the bending moment at C. And again, my suggestion is that you draw a similar little diagram, only this time from point C right across to A, and ignoring everything to the right of C, only including everything to the left of point C. And then we will then calculate those bending moments again. And again, starting with clockwise as being positive. Clockwise to the left of C, we have the 34.67 times, this time, 6 meters away from point C. That's the only clockwise moment we have again, so again I'm putting in a negative sign for it to look at anti-clockwise. And we have the 10 kilonewton point load coming into play there, and it is 2 meters over from point C, so it's minus 10 times 2. We also have the converted UDL to the left of C, which is all of that UDL of 6 meters long and 12 kilonewtons per meter. So again, it's going to be an anti-clockwise moment, and it's negative, and it's going to be converted into 72 kilonewtons, and that is going to be multiplied then by half of the length, which is where it's going to sit, the distance, half the length of that UDL, which is 3 meters. And that all, whenever calculated out, in your calculator will actually show you a minus sign, but really and truly we do not have minus numbers within actual sort of bending moments, but what we do have is positive or negative moments. So we have the answer of 27.98 kilonewton meter, and I'm just going to shift this over a wee bit. And rather than writing that minus number, we write negative behind it, and that tells us that that is a negative bending moment. And finally, the bending moment at D, and we know this from previous examples that we've done in the class, that when you work it all out, it should effectively be 0, so we're going to consider it to be that. So we've now got all our bending moments calculated out. We've got our 50.10 at A1, we've got our 42.68 at B, we've got our 27.98 kilonewton meter negative at C, and we've got 0 at A and D. So we're going to transfer those now over onto our bending moment diagram, and at A we have 0. Unlike with the shear force diagram, we don't work from the previous point every time, but this time we work every time from the 0 line. So when we look now at the bending moment at A1 here, which was 50.10, then we come down from the 0 line in the positive side of 50.10 kilonewton meter. And then for the bending moment at D, it's positive again, it's 42.68. So trying to keep it in proportion, we say 42.68 kilonewton meter. And then finally we have bending moment at C, which is 27.98 kilonewton meter, and that's up on the negative side. And finally here we have 0. So just to join those dots up, where you have a UDL it's going to be curved, and where you have a point load it is straight. So I'm just going to draw those in as our curved line as best I can, and then finally this one will be a straight line down. This is negative bending and this is positive bending, and that completes our bending moment diagram, and we'll continue in the next video.